here at the University of Montana, and a short video on Math 439, Euclidean and non-Euclidean geometry, which I'll be teaching next fall. The course description is not Euclidean geometry from a rigorous axiomatic viewpoint, and non-Euclidean geometry is chosen from Lobachevskian, projective, finite, and Riemannian. So to give you a sense of what that means, Euclidean geometry is the setting in which most of us first were introduced to geometry in high school. That is, geometry where the surface on which we construct figures is a flat plane. Non-Euclidean geometries are those that are not flat plane geometries, so where, for example, we construct figures on curved surfaces. So upon completion of the course, students will be able to construct mathematical proofs using axioms of Euclidean geometry, and then explore, conjecture, and prove mathematical ideas and theorems, develop a facility with geometric theorems and proofs through hands-on exploration, and then explain different geometries and their development through comparisons of their axioms and the validity of basic theorems in different geometries. So sort of comparison of different settings in which geometry can be constructed. So here's an example. Suppose that 4 points A, B, C, and D are placed on a circle in a clockwise fashion, and then we connect segments A to C, and then C to D, D to B, and D to A. What conjectures can we make about the resulting figure? So it sounds like we're talking about a Euclidean geometry question here. So I have the figure constructed, A to C, C to B, B to D, and D to A. We have these two resulting figures which then have intersecting lines. I've constructed the point of intersection E, and the question is, what can we say about this bow tie figure? And I can move these things around and investigate it for different values of A, B, and C in terms of where they were located on the circle. And I don't know if you noticed this, but it appears that the two triangles that are drawn are always the same shape but different size. In other words, the two triangles seem to be similar. To check that, we could show the angles of the two triangles and see if the angles are the same, and indeed they appear like they are. I have a 43-degree angle here and here, a 103 here and here, and a 34-degree angle here and here. And so it appears like indeed the two triangles are similar because they have exactly the same angles, and we'd be interested in a proof of that assertion in the course. So a good example of the type of activity we'll be conducting in the Euclidean geometry portion of the course. Well, what about a non-Euclidean example? Do triangles drawn on the sphere have angles that sum to 180 degrees? Here we're going to have to go back to the webcam and take a look at what triangles on the sphere look like. So I have here a sphere, and I've drawn a triangle on that sphere. So hope you can see that. So it looks like at first glance that, yeah, that triangle seems like a regular old triangle. I mean, maybe you'd want to get out a protractor and bend it on the sphere and try to kind of measure those angles with the protractor. But some more investigation might lead you in a different direction to say that no, things on the sphere are really different. If I put A, for example, I'm putting A right here at the top of the globe. So in other words, it's at the North Pole. So there I have A, and then I go down the globe to the equator of the globe, and I put C there, and then I travel along the equator. Well, then I can travel at a right angle along the equator to, say, another point B. And if I put B a quarter of the way, I guess, along the equator, let's see if I can show you, a quarter of the way along the equator, then what I end up getting is a triangle where, let's see if I can get it far enough away, a triangle where all three of those angles appear to be 90 degrees. And that seems to indicate that triangles drawn on sphere have angle sums that are quite different than triangles drawn on the flat plane. So a question of non-Euclidean triangles is really being investigated here, and we want to prove that their angle sums indeed are maybe can be bigger than 180 degrees. So that's about all I wanted to say about the course. I hope I piqued your interest, and I look forward to hopefully seeing you in the fall if you choose to enroll.